So let's look at wire number 1. Number 1 is going to create a magnetic field to the right of it. Okay? What direction is the magnetic field going to be to the right of this? Fingers go up, we're going to curl down, meaning we're curling into, right? So over here, there's going to be a B field going into Now what I want to look at specifically, let's look at, so I'm going to call this B1. What I want to look at specifically is at the location of the second wire. So notice on the second wire we have a current going down and a B field going into, right? And so as we just learned on Friday, when you have a current and a magnetic field, there's going to be a force exerted on the wire. So there's going to be a force exerted on the wire. So in other words, this wire is going to move. It's not going to stay still, it's going to move. Can you do your right-hand rule and figure out the direction of the force? So use the right-hand rule from Friday. Figure out the direction of the force on wire number 2. So thumb follows the current, and we're gonna move our B field into, what direction is my palm? To the right. So our B field, our force, is going to be to the right. So in other words, this wire is going to move to the right. There's going to be a net force acting on the wire to the right. So that's going to be the question here, is how much force, what is the force acting on wire number 2? So in a normal situation, you'd have to find the direction, but we already did that. So let's just find the magnitude. So we're going to start with what we did on Friday. What's the equation to find the force on a wire in a field? BIL. So we're going to start with that. F equals BIL. Now let's make sure we got our B's and our I's right. So this is the force on wire 2, right? So I can call that, I guess, wire F2. Which B am I talking about? Am I talking about the B that wire 2 is creating, or the B that wire 1 is creating? Wire 1, right? So let's call that B1. Is this the current in wire 1 or the current in wire 2? Wire 2. So what we're just looking at is this wire all by itself, right? So there's a B field we call B1, and then the current I2 moving this way. And then L, what does L refer to in this problem? Is L the 4 centimeters or the 6 centimeters? 6. So that's the length of the wire within the field. And if these are both the same sizes, you just use the length. Okay? If they're different sizes, what do you think? Would you use the larger value or the smaller value? The smaller one, yeah. Is that just a 50-50 guess, or why is it the smaller?
Oh, because it's longer, but the top and the bottom wouldn't have forces acted on.
Okay, good. So if this one was longer than 6, right, this one would only be 6, and so this would only create a magnetic field up to this point, and so only 6 would be inside the field. Okay, let's keep going. So we know B1, or we can find B1. How can we find B1? Where's B1 coming from? The magnetic field created by wire 1. So wire 1 is creating the B1. And so the way we figure that out is using U I over 2 pi r I2 times L. Which I is this? This is I1, right? So B1 is coming from current 1, right? That's what's creating the current going through here. So this would be the derived equation if we wanted to find the force between two wires. This is the equation that you would essentially use. Let's go ahead and solve it. I would prefer for you to understand the derivation and not just try to memorize these. It's going to be a little too much. So I gave you all the numbers. Let's go ahead and solve it. So 4 pi 10 to the negative 7th times I1 which was 5 times I2 which was 10 times L which is 0.06 divided by 2 times pi times 0.04 and what do we get for F2? Is that being confirmed? What direction did we say? To the right. What about wire 1? Let's kind of repeat this for wire 1. Let's do the direction first. Why don't you guys figure out the direction? You have to do 2 right-hand rules to figure out the direction. So the first thing you want to do is find the B field created by I2. So why don't you do that? At this location, find the B field from I2. What are you getting, in or out? Thumb down, curl, what direction? Into. So over here it's also into, x, x, x. And right hand, do this, the other right hand rule to find the force. Thumb goes up. B field is in. What direction is it? Left. So if you called this one F2, this one would be F1. Notice they're in opposite directions. Is this weird? No, because what did we learn from Newton? What do we know about all forces? If this pushes this wire to the right, what must this wire do? Push to the left. Which one's going to push with more force? The 5 amps or the 10 amps? Equal. They are equal forces, right? So forces are equal and opposite. So if this pushes this one to the right with 1.5, this is pushing this one to the left with 1.5. And in fact, notice if I just switch these currents around, is that going to change my end result? No, it's still going to give me the same exact result that I got down here. So wire number 2, the answer would be 1.5 times 10 to the negative 5th. No need to do all the math here. We'd be going to the left. Okay? What if these currents, so these currents were going in opposite directions. What do you think, what would happen if the currents were going in the same direction? Let's just do this conceptually. What if the currents were going in the same direction? Let's do our right-hand rule. So this one would still be going into, right? So this would be, the B field would be going into at that location. When we do the other right-hand rule, what do we get for the force? Thumb goes this way. B field goes in. What direction is the force? To the left. So this time our force would be this way. F2. without doing it, what's Newton's third law is going to tell us what direction is this one's force going to be? This way. And so the two in this case, if they're in the same direction, they're going to essentially attract to each other, and if they're in opposite directions, they're going to repel or push away from each other.